So let's begin our session. I think there was a network connectivity issue, so now I have switched my network. So I hope there won't be any issue. So let me just present my screen. So I hope my presentation is visible and I'm audible. So let's start our session for today. So, good evening everyone. Welcome to the week 10 live interaction session for the course Polymers Concept Properties, Uses and Sustainability. This course is offered by Professor Abhijit P. Deshpande sir from the Department of Chemical Engineering, IIT Madras under the NPTEL program. Myself Pratyumnan, a PhD research scholar from the Department of Chemical Engineering, IIT Guwahati, is here to conduct this live interaction session for this course. So we have almost come towards the end of this course for this particular semester. So we are already in week 10. So in the last 9 weeks we have discussed a lot about polymers and specifically speaking polymers concepts and properties, and also uses in various lectures across the 9 weeks. So, in the last live interaction session, which was held on Friday, I hope everybody will be able to remember that we discussed something more related to the polymer flow behavior, and then we also discussed about the concepts of polymerization kinetics, polymerization reactions, polymerization process. We discussed about the polymer processing operations in detail, where we went through the concept of extrusion first thing and then injection molding. So I hope those two concepts, they are very important in case of polymer processing, but again they are very simple to understand, so I hope there may not be much difficulty in understanding this extrusion process. So again, let me just give a very quick overview of this extrusion process. It typically, what we do is we take polymer pellets, usually mixed with some sort of an additive like coloring agent or stabilizers. We mix them, and once it is mixed, these polymer pellets are fed into the extruder through the hopper. So once this polymer pellet goes to the screw extruder, because of the rotational motion of this screw, these polymer pellets are carried forward, and as they are carried forward, due to the friction as well as the viscous dissipation and the external heating that is given to the screw, these polymer pellets are melted, and then the molten polymer is pushed through the screw. So once it reaches the end of the screw, this polymer melt is forced through the die, or you can say it is extruded through the die. Once they are forced through the narrow die, they try to try to achieve their desired shapes. So the die is usually designed in such a way that we give shape to this polymers or polymer melt. Again, also in relation to the extrusion process, we also discussed some of the key variables such as the rotation speed, the viscous heat dissipation. Then we discussed about the fiber breakage, and also how the screw dimensions itself becomes a factor that affects the extrusion process. So the extrusion is a kind of a continuous process. So once, and this is one of the most commonly used process to form majority of the plastic products that we use. After extrusion, what we have is injection molding. So it is basically a process in which you try to inject a polymer melt or a molten polymer solution into a mold, and then once the polymer is injected into the mold, the material So once it is injected under pressure into the mold, the sample is then cooled, and then the mold is cooled and solidified. Once that solidification process is done, the mold is open, and then the plastic product is ejected out. And then again the same process repeats for forming of different types of plastic products. Again, here also, every process if you take, there are certain variables that needs to be optimized. They can neither be high nor be too low, because if they are too high, then it has their own consequences, and if it is too low, then we may not get the desired product what we want. So here also we have two variables that we have discussed. One is the pressure, and another one is actually the temperature. So in case of the temperature, if the temperature cannot be very high, because if it is very high, then what happens is, even though it makes the flow easier, but in case of certain polymers, thermal degradation start. Polymers are very susceptible to temperature changes. Once it goes beyond a particular temperature, they are susceptible to thermal degradation. After that, so even if the temperature is too low, then the polymer solution is going to be very highly viscous. So the amount of pressure that is required to fill the polymer solution into the mold cavity, that requirement is going to be very high. So is going to be very high. So that again, so increase the pressure requirement means you need to use certain utilities to make sure that it achieves the desired pressure, so that the flow can be easy or the polymer can be filled, which is going to be energy intensive, depending upon what kind of pressure ranges we are discussing about. In case of pressure, if the pressure is too high, then the mold will overflow. And if in case if the pressure is too less, then what happens is there can be a significant shrinkage in the plastic products that you are going to form. So these are the two types of polymer processing operations that we discussed in the last live interaction session. In today's, we will continue discussing about polymer processing operations, but our focus will be mostly on the post extrusion process. So after this products are manufactured through this extrusion process, what kind of post processes are usually done on these plastic products? So that will be the focus of this live interaction session today. And of course, after that we will also discuss more about the recycling, and we will finish with recycling before we actually move on towards solving some of the problems. So this week it will be more of solving theoretical questions, where we will deal with some of the questions which will be mostly of answering them like a subjective type questions, and we will also solve two numerical problems. So that is the goal for this week. So talking about, so going on into this week 10 sessions content. So as I said, our main focus will be on post extrusion processes. So that is nothing but the shaping operations. So different types of shaping operations are usually performed on this plastic products. So what happens is, after the extrusion process, the polymer melt, which whatever you are going to form in case in this extruder, that polymer melt is actually forced, or you can say is extruded out of the die. As we discussed before, these polymer melt are going to be extruded, and that extrusion process is and that extrusion or the polymer melt is extruded out of the die that you are going to have. So these extruded polymer melts, whenever they are forced out of the die, they can actually have they can be in various different forms. They can be either in the form of films, pipes, or wire coatings, or you can say fibers or other objects like C and I section beams. Again, this all typically depends upon the shape of the die that we use. But if you see, as I said now, the shape of the die, but it is not exactly that whatever that shape that your plastic product is going to have, that shape is what that die will also have. So our common thought process is, if we are getting a particular plastic product in a particular shape, then that dye that is used to manufacture such a shape of a plastic product should also be in the same shape. So that is common thought process, as I mean, that is how everybody thinks. But in case of polymers, that extruded material or polymer, that profile or the extruded polymer shape, that shape and then the shape of the dye that is used in this extrusion process is going to be different. So they are not going to be actually same. Of course, there is a particular reason on why that extruded profile and then the die openings are typically different. So anyone, so that's what is for today's question 2 actually is. State the two main reasons for the observed difference in the profile of the final extruded material and then the dissection. Oh, sorry, and the dissection. So let me change this as make. So anyone on any ideas on why is it so that that extruded material what we have and then the dye what we use, they both are not going to be in the same shape. They basically have similar, they basically have different shapes. The dissection and then the material that you obtain, they are not going to be of the same shape. Why? I mean, what could be the reasons for that? I mean, the main reason is one, and apart from that, there is also another reason which contributes for this observed difference. So, one thing is, the very first thing is the macromolecular segmental stretching and recovery. Segmental stretching and recovery. And second one is so what actually happens is this polymer as such polymer is a macromolecule. So when they are actually going to be forced or extruded out of the die, what happens is these macromolecules undergo a segmental stretching. And once they are pushed out of the die, what happens is that that stretching actually recovers back. So this is one case, this is one thing that is something unique to polymer, because in case of other molecules you may not observe something like this, but in case of the macromolecule, because of the segmental motion or the mobility that it exhibits, this segmental stretching and recovery is possible. And this is one of the reasons why the shape is of the dissection, and then the dissection is different from that of the plastic product. For example, if we keep that whatever the die, that shape of the die as what we wanted in the plastic products, then what happens is the final plastic product that is going to come out of the die will be something completely different. It is not something what we intend. So in order to basically get a particular plastic product with a certain shape, we need to adjust the shape of the dissection. Because if the shape of the dissection is also going to be, if we are going to keep that shape as same as what we actually want in our plastic product, then because of this macromolecular segmental stretching and recovery, the plastic product that we finally get out of this extrusion process is not going to be something that what we actually intend for. So this is one of the reason, and another one reason is because of the surface tension between the macromolecule and the surrounding dye. So these are the two reasons. I mean the primary reason is the macromolecular segmental stretching and recovery. The other reason is the surface tension between the macromolecule and the surrounding dye. Because of these two reasons, there is a observed difference in the profile, or you can say shape, of that final extruded material and then the die section in the extruder which is there. So apart from this, we have something like what we discussed was the post extrusion operation. So in that you have three different operations. So one is stretching, another one is rolling, and another one is blowing. So in case of stretching, so first talking about stretching as the first post extrusion operations, what actually happens is over there we have something like fibers of film. So usually what we see is that the products that we get out of this extruder is going to be either in the form of a film or fiber or some other shape as we discussed before. So these fibers of films, that whatever that we get out of these extruder, are going to be stretched, and that stretching, depending upon whether it's a fiber or a film, is going to be either uniaxial or it is going to be biaxial. And this stretching, what it does is it helps in the orientation of the chain. So obviously when you try to pull these, or when you try to stretch the polymer, what actually happens is that the polymer chains tend to orient along the same direction. So in the stretching direction, these chain will orient themselves. So because of this preferential orientation of the chains along the direction of the stretching, what happens is that certain properties, not all, but certain properties of this polymer is going to be enhanced. So that is one of the reason why such kind of post extrusion operations are usually performed. The second one is the rolling. So over there what actually happens is you are going to use the rollers, and those rollers, the rotational motion of the rollers is going to cause the stretching in the polymer products with what you obtain from this extrusion process. Apart from that, you have also something called as blowing. So what actually happens there is air is blown into these extruded structures, which causes, so once you blow the air into the extruded structures, what happens is the structure is obviously going to expand, because that air molecules are going to occupy the space. So because of that, the structure is going to expand, and that also causes stretching. So you have some product, you try to feed that product, or you try to insert some material. So obviously, depending upon the capacity of that particular product, it is going to expand, and when it is expanding, it's going to stretch. It's something very similar to a balloon. So when you have a balloon and when you inflate the balloon, what actually happens is the air is blown into it, and then it occupies the space, and because of that, the balloon expands as we keep blowing it. The balloon expands, and this expansion actually causes stretching of the rubber walls, so, or stretching of the balloon walls. So that similar concept is also used here. So because of this blowing, what actually happens is, in case of the plastic products, this helps in shaping obviously the structure, and then it also helps to reduce the film thickness. So once the stretching happens, the thickness of the polymer walls that you have is going to actually reduce. So this becomes a kind of an advantage, that which we will see in the other operations. So this is the these are the different types of post extrusion operations. First one is stretching, then you have rolling, and then you have blowing. So in all these three cases, what we try to do is we try to stretch the macromolecule. Only the way of stretching is going to be different, but then the final purpose is going to be the same. In case of stretching, you use mechanical force to stretch. In rolling, you use rollers. In blowing, you blow the air into the into the extruded structures, and then expand them, stretch them, and this helps in the shaping of the product that we want. So this is about the entire overview of the extrusion process. So we learned what is extrusion, how it is done, the process variable that it affects, what kind of structures we get, and how to process those structures into some particular plastic shape that we want. Apart from that, we looked at injection molding. Next one, what we are going to look at is the blow molding. So something very similar to injection molding. In case of blow molding, the mold typically determines the shape of the plastic product. So this blow molding can be of two types. One is extrusion. After you extruded the plastic product, you can do simultaneously the blow molding, or you can do injection molding first and then do the blow molding. So here the concept of blow molding is something similar to the same thing what we discussed for blowing. So you just blow the air, try to expand the structure. So that same concept is what is going to be used in blow molding also. So what happens in case of blow molding is, you insert a rod or place a rod into the structures. I mean, you take a polymer melt and then you insert a rod, and then what you are going to do is you are going to stretch these polymers. So because of the stretching, what happens is there is going to be a chain orientation, and this chain orientation is going to happen along the stretching direction. After that, what we do is we actually pass gas. So the gas is blown into this material so that they actually conform to the surface of the mold. Then once that is done, the material is cooled and the mold is separated from the plastic product is separated from the mold. So the concept is very simple. You just take the polymer and then place the polymer in the mold. You insert a rod, and once you insert a rod, what you try to do is you try to stretch the polymer. Because of this stretching, the polymer chain is going to orient along the direction of the stretching. Once that is done, the gas is blown into this polymer, so that what happens is the polymer expands and gets conformally coated to the mold surface. After that, the entire system is going to be cooled, solidified. Once that is done, it is going to be separated so that the product can be retrieved. So this is about blow molding. Apart from that, there are also other operations like thermoforming, compression molding, rotational molding, and coating or calendaring. So all these operations typically is used to manufacture plastic products. The way they work will be a little bit different, but again all of them are used for processing of the plastic to get this plastic products. Again, in all of these operations, if you see in case of extrusion or injection molding, blow molding or thermoforming or compression molding or rotational molding, mixing is very important. So you need to mix this polymer, and that is not going to be as simple as what you actually observe in other kind of liquids that you use. Like, let's say for example, any two liquids that you say, like for example, any two liquids mixing, you can say water and some other easily what examples you can take, something which can mix very easily, or even if you give a little bit of turbulence or stirring, they can mix easily. But that something is not going to happen in case of your polymers. So the polymer mixing is going to be different compared to mixing of the other fluids like water and ethanol, or you can take water and acetone. So these all can easily blend or easily mix upon giving a little bit of turbulence. But in case of polymers, that is not going to happen. Again, here again the thing is their macromolecular nature, which basically prevents them from, or which basically gives them the unique uh, what do you say, unique nature, and that's what makes mixing in case of polymer a difficult aspect. So the major reason why this happens is because polymer exhibits laminar flow. Anyone have any idea on what is laminar flow? Yeah, they move past one layer by layer. So because of this, what happens is e- turbulence cannot be achieved in this case, or you cannot create turbulence in this case of polymers. So because of this, what happens is the mixing is going to be limited to the molecular and segmental motions only. Again, you can do something so called as a dispersive mixing, where these aggregates and domains are actually broken down, and this is something which we usually try to do in case of mixing a polymer with the filler or polymer polymer blends. So you try to do this dispersive mixing so that this agglomerates and then the domains are actually broken down, so that there is a uniform dispersion between the components throughout the entire system that we take for our material that we take. So this is about mixing, and they entirely about the polymer processing. Again, mixing can be done in multiple different ways. There are also equipments for doing this kind of polymer mixing, but the main concept that we need to understand here is that the polymers are kind of special class of materials, so they are not going to behave or as like other fluids that we have. They try to exhibit significantly different properties compared to the normal mixing that usually happens. The major reason why this happens is polymers typically exhibit laminar mixing, but also it's that the viscosity of this polymer is going to be more. So polymers are highly viscous materials, or you can say that when they are actually mixed in some solvent, they try to exhibit high viscosity suspensions, they try to form high viscosity suspensions. So that is one of the major reason why it is very difficult to mix a polymer, and that is also one of, you can say, the other reasons why polymers, if you see polymers, majority of the polymers do not mix. The intermolecular mixing for majority of the polymers is not possible, so they try to remain in more often in a suspended state. So that is the reason it is very difficult to uh, what do you say, kind of dissolve a polymer in a solution or in a solvent, sorry. So this is major reason because they, yeah. Mm. No, not necessarily. It should be like that. Polymers, that is again. It's basically because of their macromolecular nature. Only this particular thing happens. It need not that all high viscosity suspensions or mixtures will have laminar flow. So usually in fluid mechanics, we try to determine this whether a particular flow is laminar or turbulent depending upon the value of Reynolds number. I hope you. I mean, Are you aware of Reynolds number? Hmm. So over there, what you try to do is you try to over a flat plate, you try to um, kind of, what do you say, make that polymer solution, make any kind of fluid flow, and then based on the density, viscosity, as well as how long the solution actually moves or covers that distance, we try to calculate the Reynolds number, and then based on the value of the Reynolds number, we try to say that this particular flow is either laminar or it's going to be turbulent. Mhm. You can try to search about flow of liquids in a flat plate. So there you will try to, so there they will specifically classify whether a flow is laminar or turbulent based on this Reynolds number. Yeah, and so this is about polymer processing. Next, what we will have is the concept of recycling. So again, as much as people say polymer is good, I mean polymer is beneficial for lot of uh, you know they have done a lot of, they have given a lot of advantage, or they are like kind of advantages for the humankind, but at the same time, as much as they are advantages or they make the life of people easy, they also have their own downside. It is that they are not biodegradable. So majority of the plastic waste, whatever that gets generated, remains in the environment for long time. It can span from few days to few years to even hundreds of years, or even you can put it in a very proper way, from few days to multiple decades. So because so and this length or their lifespan varies from polymer to polymer because of the wide versatility of the polymer. So you cannot really so that is the reason why the span is going to be a very longer one. It's not a very short span of time. It can range from few days to multiple decades, or even centuries for some in some cases. And typical and one more major problem that arises is these polymers, they break down over the period of time, and then they also contaminate the water bodies as well as the land, and that has resulted in a issue. I guess everyone is nowadays aware of the concept of microplastic contamination. So people have identified that people have identified microplastic in almost all the organs within the human body itself. So there are lot of literature findings which support the fact that microplastic contamination is not just something that is there present only in case of water or land, but even since we tend to use these plastic products again and again, we are also contaminated with microplastics, and it is becoming a problem as days are progressing. So there are a lot of ways to combat this issue. So one of this possible way is to, again this we discussed earlier also, one of the possible way is to recycle or try to make polymers recyclable, or try to come up, either try to make the entire polymer itself in such a way, synthesize new polymers in such a way that one that they are recyclable, or try to find out strategies to make sure that this conventional polymers or whatever the traditional polymers that we use, they can be recycled. So these are the two different, you can say, kind of research areas itself. So this particular session will be on understanding the recycling processes, and then the certain challenges and problems associated with the recycling of this polymeric materials, or what are the challenges does this recycling face in case of polymeric materials. So typically, as I said, recycling means you try to recycle a product which was discarded as waste. So something that is discarded as waste is taken, and then it undergoes some sort of processing so that it can be used for so that it can be used the next time. So this is what is recycling. So in polymer recycling also, it is done, the concept is the same, but it is again done in various ways. So one of these ways is, so there are two types of ways to do polymer recycling. So one is primary recycling, and another one is secondary recycling. So in case of primary recycling, what actually happens is, whatever that waste that gets generated is used up for that same application. Let's say I use a plastic product for a particular application, and once it is damaged or destroyed, or once its use is over, I throw it away. Then if that waste itself can be used for the same application, or whatever that plastic waste that got generated, if that plastic waste itself can be used for the same application, then that type of recycling is called primary recycling. However, if that waste, whatever gets generated, if it is processed, and after that processing, if it is used for some other application apart from the primary application for what it was used, then that type of recycling is going to be secondary recycling. So here the plastic waste is used for the same application as in case of secondary, that plastic waste is going to be is used for some other application. It's not going to be the not the same one as before. So since in case of primary recycling we use it for the same application, so it's like a cycle, a closed cycle. However, in case of the secondary recycling, what happens is since it is used for some other application and not the same as what I have done used it for before, it is called open cycle. Again, since so that here comes a thing. So I am saying that whatever the plastic waste, if I'm going to use it for the same purpose again, then there is no issue. But if I'm going to use it for some other purpose, then whether this particular plastic waste or whatever was generated, will it be suitable for that particular application, or whatever that waste that got generated, can it be used for some other application? If yes, then for what type of application? Should it be something like you can say, can that polymer be used for something more better, or for better application, or for some other completely different applications with superior properties, or can it be used for some other applications where the performance metrics may not be too much of importance, may not be of prime importance? So that question comes immediately once we discuss about secondary recycling. So for based on that idea, or you can say that particular concept, we have two different types of recycling in this secondary recycling itself. So this is the primary classification. One is primary recycling, secondary recycling. In secondary recycling, since the final application, or since the application after recycling is going to be different, so because of that, there are two types of classification inside this. One is down cycling, and another one is oh sorry, upcycling. So in case of upcycling, what you actually do is you try to take the plastic waste, do some processes, or you can say manipulate the plastic, or manipulate that waste material, or you can use say devise some strategies and make them for some application. You can say that you try to enhance the property of the material. You try to enhance the property of the material using some strategies, so that they can be used for wider application. through different strategies. However, in case of downcycling, what happens is you try to use the polymer or the recycled product, but over there you use them for low performance requirement applications. So not a very there you do not, as I said, the performance metrics may not be of prime importance. So in that case, you call that as downcycling. So upcycling means you try to make sure that the recycled product has enhanced properties. Uh, but of course, you can try to manipulate that by using multiple different strategies, so that that particular recycled product can be used for wider application. However, if that particular plastic product or the recycled product is going to be used for low performance applications, then that type of cycling is called downcycling. Of course, can how do you, as I said, through different strategies, any idea on what could be these different strategies to enhance a property of the material? There can be multiple strategies, so any one or two from anyone.
One strategy can be mixing of any kind of additive, performance enhancing additive.
So something like you can say fillers or reinforcements, so additives, and apart from that, anything. So you try to change the molar mass distribution of the polymer, changing. So once the molar mass distribution of the polymer is going to be, I mean, if you remember the concept that we discussed in the very first or second live interaction session on the about polydispersivity index, the ratio of weight average molecular weight to the number average molecular weight. So so once you make that polydispersivity index closer to 1, then the processing of these polymers will be quite easier. So again, once you change the molar mass distribution, apart from the processing, also other properties are going to change, and that can also be used for wider applications, or it can be made suitable for applications with the higher performance metrics as well. So this is about recycling again. So before you do this recycling, you have to do pre-recycling operations as well. So that typically includes, I mean, again, these are all very something which is common to all the recycling operations as such. First you need to do separation and sorting. So in order to make that recycling process efficient, you're going to do some sort of separation, sorting, then you are going to do something like called volume reduction, so that it's not like the mass or the volume of the material is going to be so huge, then it will be difficult to do that recycling. So you try to crush it or cut it or grind it so that you can reduce the volume of the material, and also you try to clean them because you want your product to be contaminant free, or you don't want your contaminant to affect the recycling process, so you try to clean that. So these are very recycling operations is something very common to all. This is something very common to all the products that you want to recycle. So now talking about the challenges. Hmm. Hmm. No, once you have that plastic waste, so you try to, what do you say? When you recycle, you try to crush the polymer, right? So you do some sort of operation for recycling to make it so that it can be reusable. So during that time, you can obviously do some. You can obviously change the molar mass distribution through different ways that are there to make sure that the distribution changes. So if you go with the reinforcement or nanofillers, it's just about adding. But in case of the molar mass distribution changes, then that will be more often of breaking the polymer chains or trying to do some kind of treatment, like in such a way that the chains can break. Some sort of, if you say that, mm, what do you say? Some kind of you can use. I mean, one of the things that coming, some sort of lysis type reaction, like hydrolysis, or use enzyme to break the bonds, or use some sort of an acid to break the bond so that you can reduce the size distribution. So I mean, these processes, it's not like what you do to that plastic product, the finished plastic product. This usually is done during the recycling steps. So coming with respect to challenges for plastic products, so the first challenge is going to be, again, processing of the plastic products. So the thing is, there will be multiple plastic products which are going to be there, and you have to recycle them. So it all depends upon what kind of processing that we do, whether that particular recycling operation is going to be only for that plastic, or if there are also different plastics which are present along with that particular plastics, then again there are challenges that comes up, because different plastics usually exhibit different types of behavior. So if you try to heat this, so when you do this recycling operations, you try to actually do this process at high temperatures. So if you have multiple plastic products, then, or if that waste has multiple plastics of like different kind, let's say PET, PMMA, PVC, then what actually happens is the melting temperature is going to be different for all of them. Some of them will melt at very low temperatures, some of them will remain stable even at high temperatures. So because of this, what happens is there can be processing difficulties. Heterogeneity will be created in the mixture, which will create the processing of the plastic waste a challenge. Then Second one is the blending of the plastics. Since they will be of different nature, so their blending could be made difficult, because all the plastics or polymers whatever you have will not blend easily. It all depends upon their nature. Suppose if you have a, let's say, a polymer which is hydrophilic, and let's say another polymer which is going to be hydrophobic, if you try to blend them, then it may not be, the blend may not be, what do you say, will be a miscible blend. So there are chances, we have also discussed about the concept of miscible and immiscible blend. So there are also cases, if you take hydrophobic and hydrophilic polymers and if you try to blend them, the blend may not be miscible. You can also generate an immiscible blend. So that is again another one kind of issue that happens. And if you try to, let's say for one cycle, it is going to be fine, the product that you are going to get after recycling will be of good quality. But what will happen if you do this recycling operations again and again? Will that be, or will that recycled product after multiple recycle will be as good as the one that was manufactured earlier? So degradation can happen during multiple recycling, property degradation. So these could be some of the challenges that is associated with the recycling of the plastic materials. So here we end our uh, concept discussions. So we have few questions for this week. I mean, majority will be, as I said, it is going to be like kind of a theoretical ones. Two problems are there. So let's look at that one by one. But if you have anything you would like to ask me, yeah. Mm. I think there was a network issue. So let me share my screen. So if you have anything to ask, then you are welcome to ask me, or we can, if not, then we can progress to problem to these questions.
I have one query regarding the very initial part, the extruded part actually, when I was
Oh,
doing
okay,
the
okay, okay.
extrusion trial.
Hmm.
Yeah, so we mentioned
Hmm. Hmm. So, because of the differences in the surface tension of that surrounding die and then this macromolecule, what actually can happen is that the shape of your plastic product or of this macromolecule will change.
okay.
Hmm. Yeah, yeah, yeah. Macromolecule. Hmm. So the very first question is, I think, something related to what we discussed about injection molding process last session, or I can say, yeah, last session. So in injection, yeah, yeah, sure, sure. Mm. I mean, I would tell that let it is better to search for this one and then come back. There is a reason why I'm suggesting you to look at it. Please look at this, and then you can come later so to discuss about this, because the thing is, often people get comfortable with the first one, macromolecular segmental stretching and recovery in case of polymer, but it is becomes a little bit difficult when you talk about the concept of surface tension. So that is the reason I am asking you to look at it once and then come back. So the very first question is, in injection molding process, high holding pressure often leads to, there are four different options. So which one? I will it be shrinkage, or will it be thermal degradation, or is there going to be a mold overflow, or there going to be a poor weld line?
Is it thermal degradation?
Uh, I mean, here we are talking about pressure. So thermal degradation will come if we talk about high temperatures. Shrinkage, okay. But will that happen at high pressure, or will it happen at low pressure? But what about mold overflow? So when something is getting crushed or shrinked, what will happen? That plastic product will suffer low pressure, or will it suffer high pressure? So it's going to be mold overflow. And in case of this low pressure, if you have the low pressure, then that plastic product what you're going to get is going to shrink in size. So thermal degradation will happen if the temperature is going to be high, and if the temperature is going to be low, let's say very low, then what happens is, as we discussed, at low temperature viscosity is going to be low. So because of this, sorry, viscosity is going to be high. So because of high viscosity, it will be difficult to fill the mold with the polymer solution, or you can say polymer melt. So in case of the high holding pressure, it is the mold overflow. So let's come to question number 3. What is breathing? Which polymer processing technique utilizes this mechanism? I mean, this processing is something not for extrusion or for you can say injection molding. It is something that we talked about thermoforming or compression molding or rotational molding in those cases. So I'll give the which polymer processing technique. So I think that will be helpful. So compression molding usually utilizes this breathing mechanism. So why? What is this breathing mechanism, and why it is actually important in case of compression molding? So what actually happens is, in case of compression molding, you are actually going to compress the polymer melt. So what usually happens is every material will have certain air pockets. So when you try to compress, what usually happens is all these air pockets, whatever that are present, they try to collapse into, they all of them will try to collapse into each other, and because of this what actually happens is, because of this collapsing of small air packets, a bigger void will be generated. So this void generation is actually detrimental to the material, because they tend to reduce the property. So if suppose if in case of a polymer, what you actually want is the mechanical strength, and let's say if the out of the entire material, let's say 10 or 15 percentage or even 20-25 percentage of them is going to be occupied by voids, then that will be not very beneficial for mechanical strength. It will reduce the mechanical strength of the application or of the material. So in order to minimize this void formation, this breathing technique is usually used. So breathing is nothing but you try to close and open. So you first close it, you open it, the I mean to say the mold. So you first try close it, open it, and then again close it back, so that there can be a escape of gases from the material. So because of that escape of gases, this mechanism is called breathing mechanism, and that helps in the mm, I mean to for the material property to enhance. So breathing is nothing but it just open, close, and then reopen the. Close, open, and then reopen the structure. So it is used in the compression molding specifically. So let's see question 5 first before moving to question 4. So question 5 is a simple one. Which one of the following figures indicates biaxial stretching? There is figure A, figure B, figure C, and figure D. Biaxial stretching.
It's D. D.
So what about in case of A, C, and B? I mean ABC.
A is uniaxial stretching.
Mm.
B is biaxial compression.
Mm.
C also uniaxial stretching.
Yeah. So it just to this question was indented so that, so uniaxial as such means it's along one particular axis. If it is biaxial, then it will be in two different axes. So that is the primary meaning. This is uniaxial stretching. This is going to be, oh, this one is biaxial compression, because the force is compressive force here. So you don't stretch, you are trying to compress the material. That is the reason the, if you see the direction of the force, they are, they are not away, they are close to each other. They are going to like try to compress the material. So this is also going to be uniaxial stretching, and this one is biaxial stretching. So this question was fine. Now moving on to question 4. Strategies for upcycling. Again, as we so just think about this. Let's see, in case of upcycling, as we discussed, that we try to recycle the product so that their properties can be enhanced, and then they can be used for wide range of application. Inside this upcycling itself, there are two types, there are two classifications. One is called mechanical upcycling and another one is called chemical upcycling. Now we need to pick up the upcycling strategy for the following cases. So the first one is production of chemicals, fuels, or materials with high value. Which one you will go with? Mechanical cycling or chemical cycling? Similarly, you have B, C, and D, but let's first focus on A.
It is chemical upcycling. A.
Yeah, and so you are trying to produce chemicals and fuels using this plastic products. So the first one is chemical upcycling. What about the B? Separation or removal of
B.
PVC for upcycling of PET.
It is mechanical.
This is mechanical cycling. So here it is typically nothing but you're trying to sort using some mechanical means. So it's just sorting process where you're trying to remove PVC from PET. So it is basically mechanical cycling. Uses use as particulate reinforcement.
It is also mechanical, right?
So this will be also mechanical upcycling. And the final one, functionalization to improve compatibility in recycled blends.
Chemical.
This is chemical because you are doing some sort of a functionalization, which is going to be some sort of chemical processing. Uh, so that typically means it's a chemical upcycling process. So again, this question was is the same as what you actually get for your week 10 practice assignment. So that's what I've given it here. Next, let us move on to the next question. Question 6. Identify the processing operation and mention about the use of this processing equipment. Like what kind of material you actually product you manufacture out of these processing techniques.
Four is blow molding, right? Four is blow molding.
No, they all the steps are for one particular process only. It's just that there are multiple
Okay.
stages of the processing.
Okay.
So it's like the first one is the preform, then you put the preform inside the die, I mean the mold, then you insert a rod and you try to stretch the polymer, and then the fourth one is you blow gas or you blow air into them so that they can attach to the surface, the polymer can attach to the surface of the mold, and then you fifth one is you cool and solidify it, and then that part is ejected out or the product is ejected out. So which operation? Oh, sorry. Blow molding. All the steps are from blow molding. So that gets the name because of the step 4. You blow that air, or you blow the gas so that the polymer actually goes and then kind of, what do you say, conformally sits on the surface of the, or gets attached to the surface of the mold. After that, the product is cooled and solidified, and then it is ejected from that mold. So that's what you see in case of the fifth, the 5. So the sequence number 5. So mention about the use of this product, like what kind of plastic products you can obtain using this blow molding technique. Plastic water bottles, what we use. The most common example for blow molding is plastic water bottles. That is what I mean, the most common application for blow molding is to produce plastic water bottles. I think that process itself tells that only. You see, this water, this is something like a water bottle shape. So yes, so this is about blow molding. So I hope there are no confusions. So let's move on towards next question. This is about the relaxation time. Something related to the Kelvin Weigert or the Maxwell model that we saw previously in week 7 or 8. So it is given that the relaxation time of a rubber band at ambient condition is 60 days. If it is stressed to 2 megapascals initially, calculate the time that is required for the stress to relax back to 1 megapascal. I think we solved almost, if I'm not wrong, we have solved almost four questions related to this relaxation time concept in the live interaction session itself, and one or two questions if I believe I actually asked everyone to solve, like kind of out of this interaction session task. So this may should not be that difficult by now, hopefully. How to solve this problem? Just a second. So can we try to use this equation to solve the problem? So here there is nothing mentioned about the strain. So I'm going to take it that the stresses, whatever is going to be applied, is going to remain constant. I mean, sorry, the stress is the only parameter that is going to change, and the strain is going to remain constant.
Just 30 days.
Mm, I mean, did you use this equation to solve?
Um, yeah,
I
yeah,
mean,
I
like, how did
tried,
you solve
tried,
this? No, I mean, we cannot state that because we don't have any relation, right? Stating stress is directly proportional to time. Stress can be directly proportional to strain, so that is Hooke's law. And here the time is relaxation time, so that has different meaning. So since, as I said, since here we are going to take that the strain applied is going to be constant, and then the stress is the only thing that is going to vary. So Maxwell's models kind of gives a good prediction for calculate for this question. So based on this equation for constant strain applied, let's try to calculate. So it is sigma t equals to sigma naught. So since here strain is epsilon naught or E naught, what you see, E naught times the modulus, the E max is sigma naught. So times exponential of minus T by lambda is the relaxation time, or you can say it is the ratio of the viscosity to that of the Young's or to that of the modulus. So here T is directly given to us as 60. So sigma at T, that is going to be 1 megapascal, because it is asked that it the initially the rubber band is stressed to 2 megapascals, then after that the stress is released and it relaxes back to 1 megapascal. So stress at some instant of time t is going to be 1 and initially it is going to be 2. So this times exponential minus t by 60. So exponential of minus t by 60 is going to be zero point 0.5. So that is minus t by 60 equals to ln zero point 0.5 ln of 0.5, or you can say ln of 2 or t by 60 to ln 2. So t equals to 60 ln 2. So 60 times ln of 2 is how much? 60 times 0.693. Anyway, let me check that once. Ln of 2, 0.693 times 41.58 by 8. Here, since the relaxation time is given in terms of days, so here you can also write it in time, in terms of days itself. So the amount of time that is required for the stress to relax back to 1 megapascal, if it is stressed to 2 megapascals initially, it is going to be 41.58 days. So I hope this is clear. So we have solved similar problems, similar variety of problems. So you can so I hope everyone can go, if in case if you were unable to make it up for the sessions, then you can go and look at live interaction session for week 7 8. I hope during these two sessions we solved around 4 to 5 problems of different varieties. So I hope that would be helpful. We have one more questions to solve for today. So I hope there are no doubts in this one. If you have any doubts, you are welcome to ask. But for the time being, I'm moving forward. So this question is something to be about DMA, dynamic mechanical analysis of polystyrene as a glass transition temperature of 100 degrees Celsius, which is measured at a frequency of 1 hertz, and shows the damping peak at 110 degrees Celsius. If the measurement is made at 104 hertz, then the peak temperature will be. So DMA, it's actually called damping mechanical analysis. So how it is usually performed is, the polymer material whatever you have is usually prepared in the form of a cylindrical rod. This cylindrical rod is going to be attached to a circular disc at the bottom. This circular disc is going to be twisted, and after a certain amount of twisting, the disc is left free. So because of that, what usually happens is, it will obviously it is going to what do you say, twist back. So it's like a cradle. So once you twist it and then you leave it, after some time it will start to unroll, right? So it will just rotate in the backwards, and it will sort of like create a damping oscillations, so that how much ever you twist, based on that, once you let the disk free, that signal will damp, it will keep on reducing. So with respect to that, we can actually calculate the glass transition temperature. Based on this phenomena or the damping mechanism, we can calculate the glass transition temperature of the polymer. Now here it is mentioned to us that a damping peak is observed at 110 degrees Celsius, and it is measured at 1 hertz of frequency. Now, if the same measurement, or if the measurement is made at 104 hertz, then what will be the peak temperature? So how to go about solving this? We have actually solved this kind of question. One or two, I think one question we have solved for this. The clue is it is something related to how we solve the problems on WLF equation, William Landau Ferry equation. So anyone able to recollect what is that WLF equation is, or the expression for that? So let me give this equation, and so it is log alpha. I'll write the Greek letter alpha itself. Log alpha equals to minus C1 T minus the TR, that is your reference temperature, by C2 plus T T minus TR. It's alpha subscript T. Just a second. Hmm. So I hope everyone is able to remember this equation where the value of C1 is 17.44 and C2 is 51.6. So you know C1, C2, you need to calculate the value of the peak temperature. You know the reference temperature as 110. Now based on this you should be able to calculate the value of T. But the question here is how to calculate alpha, the shift factor to be specific. Alpha subscript T is the shift factor. You need to think about the concept of time temperature superposition. So over there only we try to quantify this shift factor based on this WLF equation, and then we try to solve some of the problem. We try to solve for the problem. I'll leave it here. Try to solve this question and let's see. I mean, if you are able to calculate the value of alpha t, then this question is it gets simplified. It's just a arithmetic one. So think about this question on how to solve. So for today, it is only this much. If you have any doubts, you are welcome to ask me.
Thank you for the session.
So I think I can conclude. So thank you everyone for joining today's live interaction session. So next live interaction session will be on 4th October, same 5 p.m. to 7 p.m. The lecture the live interaction session recording will for the week 9 will be uploaded by today or tomorrow, and then subsequently this will also be uploaded soon for week 10. So I thank Professor Abhijit Deshpande sir as well as the NPTEL team for providing me this opportunity to interact with you all this Sunday afternoon. So let's meet for our week 11 live interaction session next week. Till then, have a happy weekend and a week ahead. So thank you and bye.